Hey there everyone, welcome back to another video. Today we'll be looking at Physics IGCSE chapter number 6, Energy Stores and Transfers. Let's start. Energy stores. Energy can be divided into energy stores and energy transfers. Energy and energy transfers are involved in all sorts of activities. Naming energy. A moving object has kinetic energy, Ke. The faster an object moves, the greater its kinetic energy. If you lift an object upwards, you give it gravitational potential energy, which is also known as GPE. The higher an object is above the ground, the greater its GPE. This is exploited in many situations. The water stored behind a hydroelectric dam has GPE. As the water falls, it can be used to drive a turbine to generate electricity. Fuels such as coal or petrol, gasoline are stores of chemical energy. Batteries are also stores of chemical energy. Uranium is an example of a nuclear energy, which is a store of nuclear energy. Oh, sorry, uranium is an example of a nuclear fuel. If you stretch a rubber band, it becomes a store of strain energy or elastic energy. They both are the same thing. Coming? If you heat an object so that it gets hotter, you are giving energy to its atoms. The energy stored in a hot object is called internal energy. If you get close to a hot object, you may feel thermal energy coming from it. This is energy traveling from a hotter object to a colder one. It is important not to confuse internal energy and thermal energy. The internal energy of an object is the total kinetic and potential energies of the particles it is made up of. The internal energy of an object will be higher if these particles are moving faster, higher kinetic energy, or they are further apart, bigger potential energy. Heating an object gives it more thermal energy. It raises its temperature energy and this can raise it raises its internal energy and this can raise its temperature or change its state. For example, water to steam. Steam has more internal energy than boiling water, even though they are at the same temperature. The particles, the water molecules in steam, have more potential energy than water molecules in boiling water because they are further apart. Thermal energy spreads out from a hot object. Let's go to stores and transfers. Energy stores can be kinetic energy, gravitational potential energy, chemical energy, elastic or strain energy, they are the same thing, nuclear energy, internal energy, electrostatic energy. Examples of energy transfers could be electrical, thermal, radiation, mechanical. Let's go to energy stores. Energy stores are basically how energy is transferred. Let's say from a battery to a light bulb. A battery has chemical energy store. It goes from this to electrical energy transfer. From this to the light bulb, which is internal energy store. From here, it goes into two ways: radiation light energy transfer into the surroundings, which has internal energy store, and the second, thermal energy heat transfer into the internal energy store. The energy stores and transfers are associated with the battery powered lamp. The stores are indicated by blue boxes and the transfers by the green boxes with arrows. So these green boxes are energy transfers and these blue boxes are energy stores. Let's move on to conservation of energy. When energy is transferred from one store to another, it is often the case that some of the energy ends up as unwanted energy. The energy transfers in the light bulb were shown in figure 6.9. The bulb transfers light, which we want, and the heat, which is not wanted. This is an example of a very important idea, the principle of conservation of energy. In any energy transfer, the total amount of energy before and after the transfer is constant. Sankey diagrams. An effective way to represent the principle of conservation of energy is by using a Sankey diagram. The arrows show how much energy is being transferred. So from chemical energies, which could be stored in fuel and oxygen, some of it is given out into the surroundings. Some of them are used as gravitational potential energy, and some of it is used as kinetic energy. Let's go to energy efficiency. Most devices which we use, such as a lamp, are less than 100% efficient because they produce waste heat. An electrical heater is 100% efficient because all of the electrical energy is transferred to thermal energy. There is no problem with waste here. Calculating efficiency. So to calculate efficiency, we do useful energy output or total energy output. So over here we could do kinetic energy or the chemical energy. The percentage efficiency is basically efficiency times 100%. So efficiency is expressed as a number, so it has no units up to a value of 1. This number can be multiplied by 100 to get percentage efficiency. Percentage efficiency greater than 100% is impossible. So efficiency will always be below 1 or equal to 1. And when you try convert it to percentages, it will always be 100% or below 100%. Going above 100% is impossible. When the filament lamp from figure 6.16 is supplied with 100 joules of energy, it produces 15 joules of useful light. Its efficiency is thus, okay, let me use the draw. So they say it's supplied with 100 joules. That means the total energy input, that's 100 J. The units for energy is joules, by the way. It produces only 15 joules of useful light. That will be 15. And we know 15 over 100, 15 joules, by the way. 15 over 100 is 0.15. The joule and joule cancel. So, okay, this is only the percentage, this is only efficiency. When you multiply it by 100, you get 15%. That would be our percentage efficiency. Gravitational potential energy. An object's gravitational potential energy, or GPE, depends on two factors: the object's weight, which is mass times gravity. The greater its weight, the greater its gravitational potential energy. The second factor, the object's height above ground level. The greater its height, the greater its GPE. So change in GPE is calculated by weight times change in height. That's a thing. Okay, we have kinetic energy left. Okay, sorry. Kinetic energy of an object depends on two factors: the object's mass, and the greater the mass, the greater its kinetic energy. The object's speed, which is v, or the velocity. The greater the speed, the greater its kinetic energy. With the equation to finding kinetic energy is basically half times mass times speed squared, which is also written as half mv squared. Okay, so a lot of questions may come where you have to find the kinetic energy or the gravitational potential energy or the energy efficiency. But don't be scared, just remember kinetic energy equal to half mv squared, gravitational potential energy, weight times change in height, energy efficiency, useful energy or total energy, percentage will be times 100. And I think that'll be all for today's video. I hope you learned something new. Like, share, comment, and share it with your friends. Till then, see ya.